Um, next presenter is George Justison. George and I had met some years back. You were in Berlin for, I think, initial GDP meeting at the time, Malivanova. So that's when I first met George, and I thought it would be great to work together. So welcome on the stage again, George.
So thank you for joining us this morning. I have to thank Richard for asking me to review this article that was published more than 40 years ago. And I thought he was a little crazy at first when he first asked me to do that. So I hope you enjoy this journey as we kind of revisit the origins of alpha-stat and pH-stat in perfusion. And these are my disclosures. So today we're going to talk about these two strategies, alpha-stat and pH-stat, which we're all very familiar with and are all part of our perfusion vocabulary today. But let's just take a little bit of a look at the historical perspective of these blood gas management strategies and put some modern relevance to it, right? So the year is 1984, all right? And at that time, you know, they had Macintosh personal computers just coming out. The average salary in the United States is about $21,000. And I can certainly tell you that my parents thought it was crazy that this young farm kid from Ohio was being paid $35,000 to do this crazy job called a perfusionist, right? Bubble oxygenators were our workhorse in perfusion. And this term alpha-stat was just coming into the perfusion vocabulary. And Jeff Riley and I were working together. This was the first time of many times that we had worked together in our careers, and wrote this paper describing the ventilation strategy for alpha-stat and pH-stat management techniques in membrane oxygenators. And so this was a simplification of acid-base or arterial blood gas management. You know, and prior to this, you needed a nomogram or a slide rule or a calculation, right, to correct for body temperature. Blood gas machines gave you pH, PCO2, and PO2, and that was that. So let's go back and explore some of the history of blood gas technology. And this starts back in 1956, where Severinghaus was the first to describe the changes in solubility of oxygen and carbon dioxide in blood, and suggested that blood gas tensions must be made at body temperature. And he gave references and formulas for correcting blood gas results from the measurement temperature to the actual body temperature. And as you can see, he supplied charts there that not only corrected the solubility coefficients based on temperature, but also on pH. And so this was the standard at the time, right, was for us to do actual blood gas measurement at patient body temperature. Carbon dioxide transfer in artificial lungs was not really fully described until 1974. In 1962, in Galetti's textbook, he did make reference to this concept of measuring the expired gas and hooking it up to a spirometer and coming up with a measurement of the carbon dioxide content in the expired gas. But it wasn't until this paper with Snyder and Galetti, who was the senior author, that this process of bulk carbon dioxide transfer was actually described. And so this was the first basis of the description of exhaust gas capnography to describe carbon dioxide. Interestingly enough, this was in a hollow fiber membrane oxygenator. This was a Dow EDO hollow fiber, and it was made up of some 40,000 plus, fibers. And what was interesting about this paper was two things. First, this was the first time where we described changing carbon dioxide transfer using the method of changing the gas sweep rate, right? So prior to this, changing carbon dioxide was done by titration, right, of the ventilating gas, changing the FiCO2 in the ventilating gas. So this is what's unique about this paper is they describe the technique of using sweep gas only to change the bulk transfer of carbon dioxide. They also did a really good job at describing the mechanics and the design of the boundary layer effect on carbon dioxide transfer. So how blood flow rate and boundary layer conditions impact that carbon dioxide transfer. And so they came up with this description called the log mean delta PCO2, which is the difference between the delta P1 minus delta P2 divided by the natural log of the difference, or the delta P1 divided by delta P2. And P1 being the difference between the venous PCO2 and the inlet gas PCO2, and P2 being the difference between the arterial PCO2 and the expired PCO2. So this log mean delta PCO2 became the basis for describing carbon dioxide transfer. All right, so the guy in this picture holding a fish is somebody we should all know. And this is Henry Swan, okay? And Henry Swan was a native of Denver, Colorado, which is where I'm from. And some interesting facts about Dr. Swan is he was the first full-time surgeon hired by the University of Colorado School of Medicine in 1946. And some of the things that Dr. Swan is famous for is he was the first surgeon in the United States to use an aortic homograph. That was in 1949. But really his claim to fame is one of the pioneers, if not the pioneer, of hypothermia in cardiac surgery. So Dr. Swan had heard about surgeons in Europe, mainly from Russia, trying to do topical hypothermia to reduce patients' metabolic rate so they could perform intracardiac surgery. But they weren't having very good luck at preventing fibrillation during this technique. And so Dr. Swan perfected this technique in his lab where he could do topical hypothermia safely down to 32 degrees. Then they take the patient out of the ice bath, put them on a cold OR table, would prep, would drape, would do inflow occlusion so they could do intracardiac surgeries, primarily ASDs and VSD repairs, okay? And so he was famous worldwide for this induced hypothermia, and from 1953 to 1961, performed more than 600 of these hyperthermic operations. A little interesting fact, in 2007, we moved the University of Colorado from its original location to where we are now in Aurora, a suburb of Denver. But in the old hospital on 9th Avenue, there still was the cardiac operating theater that had the tiered platforms so people could stand around and watch actual surgery being conducted. And that's where Dr. Swan did his work. In 1961, he abruptly left the University of Colorado, and some people will say that's because of the invention of the heart-lung machine, right, took over the need for his surgery. But in his biography, he really explains that no, he got into an argument with the administration at the hospital because they were diverting funds from cardiac surgery to other departments in the hospital. And so he resigned and he moved to Colorado State University, and that's where he continued his work in hibernation. And so this is a lungfish. This is him holding a lungfish, which is a poikiotherm. And this is the species where he did his research on buffering systems in hypothermia, right? So this is a species where alpha-stat came from. And some quotes from his articles. These are the two articles that we were all reading in Perfusion in 1982 and 1984. The first one was the hydroxyl hydrogen ion concentration ratio during hypothermia. And then second, the importance of acid-base management in cardiac surgery. Some of the quotes from his paper is alkalinity is inotropic. Carbon dioxide added to any gas mixture is harmful, all right? And it increases myocardial acidosis, and it does not increase cerebral blood flow during hypothermia. And you must maintain a constant hydroxyl hydrogen ion ratio. And so the best strategy in his terms was this term alpha-stat, where the pH is 7.4 and the PCO2 is normal at any temperature from the blood gas analyzer, right? So at 37 degrees. So if we review our physiology, right, we all know that to be a good buffer, it has to be a substance that can both accept and give off a hydrogen ion, right? And the rate of that reaction is controlled by the pKw, or the pK of water. We know that this pK of water changes relative to temperature of about negative 0.016 per degree C. And so the intracellular concentration has to be constant with temperature, about 1. And buffer systems must be in the proper charge state at hypothermia. So his theory was that the pKw must parallel that of the pKw change of water, since we are basically 80% water, right? And the imidazole portion of histidine is the protein in hemoglobin that most closely mimics this pK change of water at hypothermia. And so you can see here the structure of histidine. And when histidine does not have a hydrogen ion attached to it, it is called the alpha imidazole. And that is where the origin of this term alpha-stat comes from, okay? But in reality, in hemoglobin, there's many substances that can act as a buffering solution, right? Histidine is just one of them. And so he chose that molecule because it most closely mimicked the pK changes of water, all right? So that's the kind of the origins. So in 1984, these papers were very influential. And so this concept of alpha-stat blood gas management, right, where we allow actual blood values to become alkalotic, right? So Jeff Riley, termed these actual blood gas values because that's what we knew them today, where it was the blood gas value at the patient's body temperature versus what he called false blood gas analyzer values, which were results at 37 degrees, or the temperature of analysis, right? So we all know today, right, that alpha-stat is non-temperature corrected values maintained in the normal range throughout hypothermia. Okay. So we also introduced this concept of the respiratory quotient, or the RQ. And in the sake of this paper, the RQ means carbon dioxide transfer in the lung compared to oxygen transfer, right? So in pH stat, as we cool, the CO2 content increases based on increasing solubility with the decreasing temperature, right? In alpha stat, we have a constant respiratory quotient during cooling and rewarming. Interestingly, this study that we based this paper done was done using the COBE CML oxygenator. And so the Kobe CML oxygenator was one of the early polypropylene oxygenators on the market. Like I said, at that point in time, a bubble oxygenator was the majority of our workforce. And this was a novel device because it had a hard shell venous reservoir, which we were all used to using with a bubble oxygenator. But it was a folded polypropylene sheet membrane. And so the ventilation strategy for this oxygenator was to keep a constant sweep rate at 10 liters per minute. And you controlled the PO2 by changing the FiO2, and you controlled the PCO2 by blending carbon dioxide into the ventilating gas, or controlling the FiCO2. So in this paper, we described the ventilation strategy. Here you can see what a pH stat management strategy is, where as you're cooling, you increase the FiCO2 to compensate for the increased solubility of the gas. And then during rewarming, you have this hyperexpression of the carbon dioxide by decreasing the FiCO2. Right? And this is what we're doing today as well in pH strat, right? But we're doing this by controlling the sweep gas, not by controlling the ventilating gas concentration, versus the alpha stat strategy, where these respiratory quotients are constant, right? Both during the cooling phase and during the rewarming phase. So oxygenator RQ is constant in both of those cases. The FiCO2 decreasing with cooling and increasing with rewarming to maintain that constant CO2 content. So this is the final description then of carbon dioxide transfer that we proposed at this time, that carbon dioxide transfer, the VCO2, right, is equal to the diffusion coefficient, right, times the concentration gradients divided by the distance, right? And assuming that temperature and solubility are constant, the above equation, it's rewritten there as equation number 6, which is basically the diffusion coefficient times the log mean delta PCO2 divided by distance, right? And so this also incorporates some boundary layer phenomenon, which we're going to discuss a little bit later. So the importance of respiratory quotient, right? So respiratory quotient, again, carbon dioxide transfer divided by oxygen transfer. Under constant conditions during cardiopulmonary bypass, with the oxygenator being the only ventilation mechanism, the respiratory quotient now becomes the anaerobic versus aerobic respiration balance, right? So the carbon dioxide transfer and the oxygen transfer become reflective of the patient, right? And so this is important today because we know that respiratory quotient can give us some important information into this anaerobic aerobic balance in patients in goal-directed perfusion. It's one of our parameters that we look at in GDP. Okay. And so today, through exhaust gas capnography, we calculate carbon dioxide transfer by looking at the expired gas PCO2 times the gas flow times a correction factor, right? And this correction factor takes into standard temperature and pressure of a dry gas, right? So a lot of formulas you'll see use a correction factor anywhere between 1.15 and 1.315, right? So at 32 degrees and an ambient temperature of 18 and a water vapor pressure of 18 millimeters of mercury, the correction factor is 1.15. But at 37 degrees, it's 1.315 under those same conditions, right? So that factor really should be variable based on what your actual patient temperature is. So the implication for this in modern oxygenator management is that every oxygenator design will have its own baseline respiratory quotient, right? Because that respiratory quotient, the impact of the ventilating sweep gas, is dependent on the boundary layer phenomenon of the design of that oxygenator, right? And this is an example of that. This is a comparison of our own data looking at an Inspire oxygenator versus an NX19 oxygenator. And this is the mean gas to blood flow ratio required to give you a PCO2 of 40 millimeters of mercury at 37 degrees. And you can see that there's significantly less gas to blood flow ratio in one device compared to the other. That doesn't mean that one device is better than the other. It just means the design and the boundary layer phenomenon impacts that required ventilating gas, right, that you need, the required sweep rate that you need. And so as a result, you have to, account for that. So now the controversy is, what was the right thing to do? What was the easy thing to do? Let's get into some disruptors that happened in the 1990s. And the first disruptor paper was from Richard Tolman. And this was, we all know Richard Tolman as the founder of biomedical simulation and the Califia simulator, right? But Richard is also an excellent physiologist and biomedical engineer. And Richard disrupted this alpha stat theory by saying that there are multiple mechanisms for controlling the pH in tissue, and that the extracellular pH has really little to do with the intracellular pH, because there's mechanisms, multiple mechanisms for ion exchange across this tissue. And so this concept of relative alkalinity that Swan had proposed was really kind of bonkers, because in histidine, there's multiple molecules of histidine, and they all have a pK range of 6.07 to 8.48. So in a large pH range, those pKs were constant. And so he said that what was more important in alpha stat and pH stat was not the pH management, but was how it impacted reduction in metabolic rate and cerebral blood flow manipulation. So what we really know is these two patients are not the same, right? So how we treat kids and adults, not the same thing. The other thing that Swan, that we know, got wrong is we do know that PCO2 does impact cerebral blood flow, right? And so that this is probably a better mechanism for the use of those two strategies. Some of the other disruptor papers from the 1990s were done mainly in pediatric surgery. And, a lot of these papers that were disruptors in the 90s, I think would be hard to be classified as evidence today, because a lot of them were small studies done in piglets. But there were several good studies, Boston Children's Hospital, that showed that using pH stat, you had greater cerebral blood flow, better cooling rates, and better recovery of ATP. Work out of Duke showed that in deep hypothermic circulatory rest, when you compared different strategies, that there was better cerebral metabolic rate recovery if you used pH stat during the cooling phase, then converted to alpha stat prior to circulatory rest, and used alpha stat in the rewarming. So there's a lot of disruptor papers that came about in the 1990s demonstrating a potential benefit. More recently, in 2010, this was a good review article, 206 papers on alpha stat versus pH stat. 16 ultimately made their cut. When you look at cerebral metabolism and deep hypothermic circulatory arrest slightly favors alpha-stat, but 4 papers found no different. Neuropsychological outcome, no difference. Outcome in pediatrics kind of favors pH-stat. Outcomes in adults with no deep hypothermic circulatory arrest favors alpha-stat. So, in conclusion, pH-stat, some things you need to remember is reduced oxygenator respiratory quotient during cooling, inflated respiratory quotient during rewarming to reach normal values at normothermia. So if you're using pH-stat, your oxygenator respiratory quotient does not equal patient respiratory quotient. In alpha-stat, constant oxygenator respiratory quotient, both during cooling and rewarming, and it is reflective of changes in the patient respiratory quotient if your PO2 and PCO2 are controlled. So makes a good argument for servo regulation, right, of PO2 and PCO2 today. So your best strategy really depends on the age of the patient, the type of procedure being formed, and the amount of cerebral suppression that's required. So thank you for the opportunity to take you through that little history of alpha-stat and pH-stat.
I wish we'd have more time. We could have listened to that for another 2 hours. So it was a great talk, George. So we have time for 2 questions. Maybe there's one question you said from the chat, or and then.
So a question from the chat is, oops. It's gone.
We can't keep up with everybody saying great talk, so we're just trying to find the question again because it's all gone.
From Vince, on as far as that's not it.
It keeps moving. What temperature do you switch methods in pediatrics?
Well,
Do you have a specific target?
Yeah, I'm not the person to answer that because I'm not a pediatric perfusionist, but I will tell you in our adult practice, it's dependent on the procedure that we're doing. So if we're doing a planned circulatory arrest, which we normally do in aortic surgery at 28 degrees, we will pH-stat going down, then we'll switch to alpha-stat just prior to arrest, and then do alpha-stat on the way back up.
Any more questions from the audience? One more, maybe, or from the chat?
Just lots of praise and thanks for adding Jeff Riley's name for the memory.
Absolutely. Thank you.
Well, I think there's nothing to add to that. So thank you very much, George. And yes.